Okay. Hi, good afternoon, everyone. It's 2 p.m., so we shall begin. For today, we have a very good speaker, very experienced speaker, a lecturer from University Technology Petronas. She will be talking about unconventional hydrocarbons and the potential of it. So, Ms. Maslin has been lecturing with UTP for quite a number of years right now, and she's very well versed in terms of petroleum engineering subjects, as well as even going into detail about a lot of research on flow assurance. So, without further ado, let's welcome Ms. Maslin from UTP.
Okay, Assalamualaikum, a very good day to all. Okay, my name is Mazlin. So I've been lecturing with UTP until I think since 2005. So about 15 years now, quite a number. Okay, my area is actually gas hydrate. So that would be basically the major part of the presentation for today. And before we go in depth, I would say in depth, okay, for gas hydrate production. So basically, we are going to be introduced to what is unconventional hydrocarbons. Okay, and I think that's enough for the introduction, I guess. So if you want to ask me anything, so you can just, write in the private chat. So I'll try to address the questions after the presentation. Okay. If I couldn't, okay, so I'll just take note of the questions and answer it later and get back to Ms. Harbin. Okay. All right. So can we start? I can share my presentation now, Ms. Harbin.
Yes, you may begin.
Okay. Okay. Okay, can you see this now?
Yes.
Okay. Try to enlarge it. Okay. Okay. So for today, we are going to talk about gas hydrates, basically. So whether it's a good future energy source. Okay, and these presentations, okay, all of the figures, okay, are taken from the websites, okay, from the reference books, and I've give proper citation down below the each figures and each statement. So if you want to go and seek further information, you can go to the website. Okay, right. So this would be my presentation outline. Okay, I'm going to basically introduce you to what is unconventional hydrocarbon. So we are going to look at definition of unconventional hydrocarbon, where we can find unconventional hydrocarbon worldwide, and we look at the overview of different unconventional hydrocarbons. So I'm just going to address only four, okay, for today. So we are going to look only at shale gas, tight gas, coal bed methane, and also class 3 or gas hydrates. And then we are going to go a little deeper, okay, on gas hydrates. So we're going to be introduced to what is gas hydrates, where can we actually find gas hydrates, and could it be a great source of energy, and how to produce natural gas from class 3s. Okay? Right. Okay. So unconventional hydrocarbons is basically hydrocarbons, okay, oil and gas, which requires extraction methods, which are basically complex than the conventional extraction of hydrocarbons. So these four types, okay, the previous four types of unconventional hydrocarbons I'm going to address is basically requires extraction methods, which are different from the conventional extraction of hydrocarbons. Okay? This is actually the examples, okay, of the extraction method, okay. Okay, examples of the conventional and unconventional reservoir types. Okay, we have say, let me take pen. Okay, so this is where we can find our coal bed. Okay, coal bed methane. And this is basically our conventional oil and gas, where we have a gas cap, okay, heavily use of oil. And then this is also where we can actually find our conventional gas, okay, and this is where we could find a tight gas, and this is oil and gas-rich shale. So we can actually, let's say, produce or extract shale gas, okay, and shale oil. And then you'd also find class 3 gas hydrates. Okay, gas hydrates we usually found at the area where we have a low temperature and high pressure conditions. Okay? And example of the extraction methods used, okay, basically are a combination of commonly used conventional methods. Okay, for example, if you want to produce shale gas, okay, they actually combine horizontal drilling and hydraulic fracturing or fracking, as they call it. Okay? And you can find actually for good illustration, okay, you can go to a National Geography. Okay, there they actually have an interesting activity on how they could actually simulate the process of extracting shale gas. Okay, you could try that. Go to the website www.nationalgeographic.org, and then for tight gas, okay, tight gas, okay, they use usually deviated drilling or horizontal drilling, okay, to expose as much as possible of the reservoir. Okay? So the greater amount of gas well drilled, okay, the greater amount of gas will be able to escape the formation. So they are using actually fracking also. They use fracking to break the rock, okay, to increase basically the permeability. Okay, and then they are actually pumping down acid. Okay, so they use acidizing to dissolve limestone, okay, dolomite, calcite, cement between the sediment grains of the reservoir rocks. So it's basically to increase the permeability of the tight sand, where we can actually find the tight gas and tight oil. Okay, and for coal bed methane, okay, they're actually drilling in or putting a steel case hole. Okay, it is drilled into a coal seam, okay, at the underground, okay, and they are actually pumping out the produced water, okay, through tubing. So it's actually reducing the hydrostatic pressure inside the coal seam. So when the hydrostatic pressure is decreasing, so so the methane gas can actually escape from the coal seam. So the gas is dissolved, okay, and going up into the surface. Okay, then let's look at the. Okay, this is basically the map, okay, showing discovered unconventional oil and gas basins around the world. So mostly the unconventional hydrocarbons are found onshore. Okay, so you can see that, okay, all this, okay, this area, okay, these are onshore fields. Okay, and then in Southeast Asia, okay, we have few more in basically Indonesia, and we can actually find some gas hydrates in Japan, okay, areas, and we have shales, okay, in Australia, okay, and we have a lot in basically in US, in Russia. Okay. So this is basically a map showing where you can actually find unconventional oil and gas basins around the world. Okay. So fortunately, I couldn't see any questions in the private chat, so I'll address it after the presentation. Okay. Okay. So this is basically the amount, okay, of gas, okay, of unconventional gas, okay, that is being estimated, okay, around the world. Okay, for example, in Australia they have shale gas. Okay, you have shale gas here, and they have a tight oil. Okay, so shale gas they have about 12.2. Let's say this is trillion cubic meter. Okay, and we have a tight oil with 16 billion barrels, which is, I think, a very large values. Okay, in Japan, okay, they have an LNG. In Japan, in China, they have shale gas, they have tight oil, and also in Russia, Iran, and probably most around the world. But unfortunately, in Malaysia, we are still actually focusing on conventional oil because we still have a lot of reserve. And I think the only for gas hydrates, basically the only locations that they found in Malaysia is at the Sabah Basin. I think it's area Gumusut Kakap Field, okay, in Sabah Basins. Yeah. Yeah. Okay, so let's go. Just this is very I mean, like, brief, okay, explanations on different types of unconventional hydrocarbons. So this is basically how shales look like. Okay, so this is when we talk about shale gas or shale or oil, it is actually referring to hydrocarbons that are trapped within shale formations. So shales is basically a fine-grained sedimentary rocks that can be rich sources of petroleum and natural gas. So in order for it to produce, okay, from the shale gas or from the shale formation, so that's why we need to use horizontal drilling and also hydraulic fracturing. It's due to the nature of the formation. Okay. And then this is how a tight gas looks like. The tight sand, basically, it's not a tight gas, it's tight sand where the tight oil and gas resides. Okay, this is taken from Energy, usgs.gov.gov. Okay, tight gas is basically the term commonly used to refer to low permeability reservoir that produce mainly dry natural gas. So when you produce gas from a tight sand, okay, you are actually producing a dry natural gas. So tight gas, okay, it can also be trapped in sandstone or limestone formations that are typically impermeable or non-porous, and it is also known as tight sand. So that's why to produce gas and oil from tight sand, that's why we are using basically deviated drilling, and we use hydraulic fracturing and also oxidizing. Okay. Then this is coal seams. Okay. And coal-bed methane is basically an unconventional form of natural gas found in coal deposits or coal seams. Okay, so this is the picture is taken from American Association of Petroleum Geologists. Okay. So as I explained before, so in order for us to actually take the methane out from a coal bed, from a coal seam, okay, we need to actually drill a steel case, okay, hole into the coal seam, and taking out the produced water, the groundwater, pumping it out, and it's going to basically reduce the pressure inside the coal seam, and the gas, okay, the methane gas is going to be dissolved from the surface of the coal seams and going to be produced. Okay. All right. And now we go to basically gas hydrates, and this is technically my area. I've done quite a few research and wrote quite few papers on gas hydrates. Okay? Gas hydrates or clathrates is basically defined as insertion compound formed from water and light hydrocarbons. So basically, gas hydrate, you need to have gas. Okay, you have light hydrocarbons, mainly methane. It can be ethane and propane also, and it was encapsulated, okay, with water cage. Okay, water molecules surrounding it inside the cage. Okay? So the whole structure is stabilized by interactions between water molecules forming a lattice and the gas molecules which is contained within the lattice at high pressure and low temperature. So in order for gas hydrates to form, these two conditions must be fulfilled. It must have it must be at the high pressure and low temperature condition. So gas hydrates is basically exist in a crystalline ice-like solid molecules, okay, and it is basically altered by the addition or existence in water molecule inside the system. So if we have a different gas molecules, the structure is going to be different. Okay? Right. And this is the gas hydrates resource map. Okay? So the yellow dot, okay, all the yellow dot is where it is actually there are gas hydrates that is successfully recovered, and the red dot is all the inferred hydrates, and when they use a PSR, okay, it's a seismic reflections, okay, to basically calculate or determine the resource estimates. And the black dot is all the drilling expeditions that have taken place in order to quantify or to verify and validate the existence of gas hydrates resources. Okay, and then it says total resource estimate of gas hydrate. Okay, I think in 2016 or 2017 is around 250,000 to 700,000 trillion cubic feet of methane. So it is a very large enormous values. Okay, and okay, to what it says illustrate the amount of energy, okay, that is contained inside the gas hydrate. So if you brought to surface, okay, 1 cubic meter, 1 meter cube of gas hydrate, okay, if it brought to surface, it will release around 164 cubic meter of natural gas. So it's about 164 times larger than the original volume. Okay? So basically, what are gas hydrates? Okay, so these are basically gas hydrate structures. We have three different types of gas hydrate structure. So we have structure 1, structure 2, and also structure H. Okay, and we have for, let's say, for structure 1, okay, the gas molecules is usually we have a light hydrocarbons like methane, ethane, and also carbon dioxide. Okay, and this gas molecules is actually residing, okay, inside the or in the middles of the structure, and the water will basically surround the gas molecules. Okay, so for structure 1, okay, so basically there are two common forms of gas hydrates, which is structure 1 and structure 2. Okay, structure and this is actually being investigated using X-ray diffraction method by Steckelberg and Mueller, and long time ago in 1954. Okay, they found that the unit cell of structure for structure 1 is about 12 Armstrong, consisting of, okay, they have a 46 water molecules with 2 types of cavities. So they have, yeah, this is 2 types of cavities. Okay, we have 2 small cavities, okay, which is pentagonal dodecahedra. Okay, this is this one. Okay, pentagonal. Okay, and they have 6 large cavities, okay, which tetradecahedra. Okay, so together with this, okay, they become 2, 6, 5, 12, and 6, 2. Okay, 5, 12, have 2, and then 6, 2, and then they have 2 opposite hexagonal faces. Okay, and 12 pentagonal faces. Okay, so they have 2 hexagonal. Okay, that's why the 2 and 6, and they have 12 pentagonal faces. That's why you have a 5, 12, and 6, 2. Okay, and that's made up a structure 1 structure 1 gas hydrates. And then for structure 2, okay, the size is about 17.3 Armstrong, okay, with 136 water molecules. So for structure 1, it only has about 46 water molecules encapsulate the gas molecules, but for structure 2, it has 136 water molecules. And it has also two types of cavities. Okay, and we have 16 smaller cavities. Okay, 16 smaller cavities like this, small. And we have 8 large cavities. Okay. And it has 4 hexagonal faces. Okay, 6, 4, and 12 pentagonal faces. And this made up a structure to gas hydrates. And the gas molecules for structure 2 hydrates is basically propane and isobutane, means the larger molecules of larger hydrocarbons molecules. Okay? And then we have a new structure. Okay, Rick Mister found it in 1987. Okay, it has about 34 water molecules, encapsulate the gas molecules, and it has about 6 pentagonal faces. Okay, 6 pentagonal faces, and have 3 hexagonal faces. It has 8 3 5 1 2 cavities. Okay, 2 new faces, and also 1 new large cavities. Okay, so for structure H, okay, it has a combination of gas molecules. It could have a methane plus neohexane, or it could be methane and cycloheptane. Okay, because they're larger molecules, so it has it form a structure H. Okay. Molecules. Okay. Okay. Sorry. Then there are basically 2 types, okay, of methane hydrates deposits that can be found in the world. Okay, the first one is actually it can be found in the ocean deposits. Okay, and in another one is Arctic deposits. Okay, all right. So methane that forms hydrate, okay, it can basically be both biogenic, okay, or thermogenic. Okay, biogenic methane is basically created by biological activities in sediments. Okay, it forms within the hydrate stability zone. Okay, and it actually sips and settles inside the gas hydrate stability zone. Okay, and for thermogenic, okay, it is created by geological process deeper within the Earth's crust. Okay, and it requires a very high temperature, so it is basically produced at a greater depth. Then it will migrates into the hydrate, and the gas produced will be migrating into the gas hydrate stability zone. Okay, so there are basically 2 types of methane hydrate deposits. Okay, we have ocean deposits. Okay, which is located below the seafloor, and we have the Arctic deposit of permafrost that deposits that above and below the lower limit of permafrost. So if you have a ground, okay, permafrost, you have a frozen ground surface, okay, the gas hydrates, okay, the gas methane hydrates is basically located below the frozen ground surface. Okay. So hydrate deposit, it can be about 300 to 600 meter feet thick, and it can cover a very large horizontal area. Okay. Okay. Okay, this is basically the phase diagram, okay, for methane hydrate formation. So as you know that methane hydrates will only form at the very at high pressure and low temperature method. Okay, so it says that, okay, if hydrates, okay, will only form within this boundary. Okay, this is basically the hydrate gas phase boundary. Okay, outside of the boundary, you couldn't find any gas hydrate, so you can only find either methane gas plus water if the temperature is larger than or greater than 0 degrees Celsius, and if it's below than 0 degrees Celsius, you can only find methane gas and on ice. Okay, but inside, okay, inside the boundaries, okay, the areas, okay, within these boundaries, you can find either methane hydrate plus ice or methane hydrate and water. So if it's above 0 degrees Celsius, you can find methane hydrate plus liquid water. If it's below, then you can find methane hydrate plus liquid plus ice. Okay. So for example, okay, if you have let's say a condition, okay, formation conditions of 12 degrees Celsius, the temperature is 12 degrees Celsius, and the pressure is about 100 atmosphere. So it's basically okay, located here. So in this area, you can find methane hydrates plus water. Okay. All right. Am I talking too fast? I couldn't see the comment. Okay, so I do not know any feedbacks. Okay, from you guys. I'm sorry about that. Okay. Right, and this slide is showing a methane hydrate stability zones for both permafrost and also ocean deposits. Okay. So under the permafrost again, okay, for this one, okay, this slides. Okay. Okay. So the hydrate formation requirements restrict the occurrence of natural gas hydrates to two types of geologic locations. Okay, first is basically under the permafrost in the polar continental shelves and also in sediment beneath the ocean floor. So the blue section, okay, here the blue section, the black curve, okay, this black curve, okay, this curved, okay, shows the temperature profiles for various water depth. Okay, so this is the graph of depth versus temperature. Okay, and this red line, okay, the red and orange line, okay, it shows the methane hydrate stability relative to the temperature and pressure. Okay, and this blue area, okay, is the blue area between the both curves. Okay, it represents the area of methane hydrate stability zone. Okay. Yeah. So methane, okay, the predominant component of natural gas, okay, it forms hydrate, okay, in the presence of water, low temperature, high pressure. So alternatively, when the temperature is increased, okay, or the pressure is decreasing, so that the hydrates are now outside of the gas hydrate stability zone, okay, they will dissociate and become methane gas plus water. So in order for you to find, okay, in order for hydrates to form, it needs to be inside this blue area. Okay, so this is for permafrost and this is for ocean. Okay, deposits. Okay, so if you have lowering in low pressure conditions and high temperature conditions, okay, this area is going to move and your gas hydrates, okay, inside this is no longer inside the regions, so it's going to dissociate and it will become only methane gas plus water. So this is basically the ideas of how people got the idea of to produce, okay, methane hydrates. Okay. So we're going to look at natural gas hydrates production methods. Okay, there are basically 4 natural gas hydrate production method, but there are only 3 types that is basically well known, and the last type, okay, is actually still in research phase. And so we are going to look at the methods, okay, one by one. So basically, how can we produce gas hydrates? Okay, that would be the questions. Okay, there are methods being developed, okay, by researchers, and some has reached into drilling stage now. Okay, and drilling and exploration well to basically confirm the existence of methane hydrates in the area. Okay. And to evaluate also the amount of reserves available. And the principles, okay, behind these production methods as basically is to shift, okay, to shift the initially stable gas hydrates, okay. So you want to bring the gas hydrates outside from its stable regions, okay. So that is the only way we can actually produce the gas hydrates. Okay. So it is basically done, okay, by three methods. Okay, first is by lowering the pressure, and another method is by increasing the temperature of the formation. First is lowering the pressure of the formations. The second one is basically eating the formation temperature, and the third one is by injecting chemicals or inhibitors into the gas hydrate bearing area. Okay. So from this graph, okay, so this is basically the stability zone, okay, of methane hydrates at this area, okay, relative to the pressure and temperature conditions, okay, in order to produce. So we need to bring the gas hydrates, okay, to go outside of its methane hydrate boundary. So by lowering the pressure, or what we call as depressurization method, okay, so we are going to actually push this to this area, okay, so that the methane gas hydrate can be produced. Similarly, okay, we are increasing the formation temperature, so we are actually increasing the temperature so that this, okay, operating condition is bring out here, and we can actually produce the methane gas. We can actually produce the gas hydrates to get the methane gas. Okay. Right. And we have these are the three gas hydrates production methods. Okay. Okay. The first one is depressurization. Okay. And the second one is thermal injection method, and we have inhibitor injection method. So this method is basically manipulating the pressure and also temperature, and we are adding in thermodynamic hydrates inhibitor or kinetic hydrates inhibitor into the gas hydrate bearing area. Okay, so let's have a look at depressurization method. Okay, so the pressure, okay, the pressure. So two methods of actually that we can actually do for depressurization method. The first one is actually drilling a well, okay, in the free gas zone. Okay, so when the gas is produced, okay, when the free gas is produced, it lowers down the formation pressures. Okay, so we have a pressure drawdown here. So this hydrates, okay, at the middle area, it's going to dissociate due to the lowering in pressure, and thus it's going to go to the free gas zone and also flows out to the surface. And another method is actually by installing a pump, okay, downhole. Okay, and the pressure is actually reduced by that. Okay, so as the bottom hole pressure is lower, okay, than the equilibrium pressure or gas hydrate equilibrium pressure, so the gas hydrate in the reservoir will dissociate, okay, and it releases natural gas along with the first it will target the area within the wells, okay, but as more gas is being produced, okay, to the surface, okay, it subsequently lowering down the pressure. It is quite distance from the well, so it's going to start producing from the area, okay, along the or near the well bore, and set far from the well bore. Yeah. So it says that if you have more gas being produced, okay, it will actually lower the natural gas hydrate saturations. So the effective permeability to fluid, okay, will increase. So more gas can be actually be produced, okay, from the gas hydrate. So you are going to get a better, like greater volume of gas produced at the area quite a distance from the well. See? So basically, the pressurization method is done by lowering the pressure in the free gas zone beneath the hydrate stability zone inside the well to dissociate the methane hydrates. So that would be the first method. Okay. All right. So then we look at thermal injection method. Okay. Thermal injection method is basically as the name goes, right? Okay. So it's basically we are introducing heat, okay, in the form of injected steam or hot water or another heated liquid directly, okay, or indirectly via electric or sonic means, okay, to the hydrate stability zone to raise the temperature, causing the hydrate to dissociate and then releasing the methane gas. Okay. Okay, promoting the gas hydrate dissociation by increasing the temperature of the reservoir, okay, we can actually do that by two methods. The first one is thermal methods, okay, which includes the thermal stimulation and also thermal flooding. Okay, so for thermal stimulation method, it is basically aiming at increasing the temperature, okay, in the vicinity of the well around this. Okay, so this is the vicinity of the thermal stimulation. Okay, so it is done by actually injecting in, okay, hot water using hot water circulation, or we use a wellbore heating. Okay, so for hot water circulation, okay, we basically circulate the hot water into the wellbore. Okay, so that's what it is, injecting the hot water into the wellbore, okay, to basically increase the bottom hole temperature. So when we increase the bottom hole temperature, so hydrates is because we have an increase in temperature in the gas hydrate bearing zone. So it is we actually push it out from its stability zone, so it's going to be produced. Okay, and for wellbore heating, okay, we are installing, okay, they are installing heater or multi heaters installed inside the dump hole, okay, and to basically increasing the near wellbore temperature. Due to the increase in temperature, so the gas hydrate is going to be dissociates. Okay, and another method is what we call as half and puff. Okay, half and puff is basically when we have injection well and also producing well, okay, production well, and then we are injecting steam, okay, or hot water into the injection well, and that's what we call as half. Okay, injection of water into the injection well is what we call as half, and then we shut in the well, okay, for some times, okay, so that to allow for heat transfer, okay, from the injection well to the producing well. So the efficient heat transfer, okay, the heat transfer that happens will actually dissociate the gas hydrates in between the injection well and also producing well. Okay, so the gas which is being produced, okay, between the wells is going to be produced through the production well, and this is what we call as puff. Okay, is either that, or we can only use also use only one well. Okay, one well. Same thing. Inject the where it says hot water, shut in the well, so it's going to basically transfer the heat into the surrounding gas hydrate bearing areas, and we can actually produce it using the same well. And this is what also we call as puff. So that's why it is called half and puff method. Okay, and then we have a thermal flooding. Okay, thermal flooding is basically injecting hot water. Okay, this is what when we have a two producing well. Sorry, the first one is half and puff. We only use one well. My mistake. Okay, so the thermal flooding is where we actually use two wells. Okay, injection well and also producing well. So we inject it says steam, so hot water inside the injection wells. Okay, so that we decrease the temperature towards the producing well. So all the gas hydrates in between the two wells is going to dissociate. Okay, and it's going to be produced through the producing well. Okay, this is the correct explanation. I'm sorry about that. Okay, right. So we have for thermal injection, we have basically thermal flooding and also thermal stimulation. So thermal stimulation, we are using hot water circulation. We use a wellbore heating, and also we use a half and puff technique. Okay. All right. And this is basically the third method of producing gas hydrates. Okay, right. Okay. which is the chemical injection method or inhibitor injection method. There are basically two types, okay, of hydrates, gas hydrate inhibitors. The first one is thermodynamic hydrates inhibitors, where we have methanol, glycols, and the second one is when we have a kinetic hydrate inhibitor. We have about PVP, PVCAP, polyvinyl propylene. Okay. And for this method, okay, for example, if you use as the figures here, okay, methanol, okay, the chemical or thermodynamic hydrates inhibitor, such as methanol, glycols, is injected, okay, it is injected into the gas hydrate bearing zone. And this will shift the equilibrium condition of the gas hydrate stability zone. Okay. So it will shift the gas hydrate, you know, the gas hydrate curve just now, the gas hydrate boundaries. Okay, it will shift it to high pressure and low temperature site where the natural gas hydrate is automatically dissociated. Basically, you are actually shrinking the gas hydrate stability area. So if the gas hydrate resides, okay, outside of the gas bearing hydrate because of the shrinking process just now, so it is automatically dissociates to get the methane gas. Okay, all right. Okay, and the last method, and this is quite this is a new methods, okay, a new methods that was being researched, I think, quite extensively nowadays, okay, because we have issues on carbon dioxide. Okay, so our fields are producing a lot of carbon dioxide. Okay, so we are producing sour gas now, so instead of sweet gas. So this is basically an alternative method, okay, that we can actually do two things at once. The first, we can actually produce or get the new energy, okay, the new fuel. We can get methane, and we can actually sequester or we can actually capture the carbon dioxide and put it inside the formation. And this also helps to actually reduce the slope instability, because you know that when we are starting to produce methane, okay, methane from the methane gas, okay, there is bound to be instability inside the formation. So it's going to be a slides, okay, and it's going to be collapsing formations because of the this is the production of methane, okay, production of methane gas between the methane hydrates in the formation. Okay, so the idea of carbon dioxide methane replacement, okay, arises because naturally, okay, carbon dioxide is easily formed compared to methane hydrates, okay, compared to natural gas hydrates. And carbon dioxide is the preferred, okay, is the preferred, actually is the preferred hydrate former rather than methane hydrates when we have a conditions below than 10 degrees Celsius. Okay, so it is feasible, okay, it is feasible to basically spontaneously replace, okay, methane with carbon dioxide without introducing external energy. And furthermore, okay, carbon dioxide formation is actually an exothermic method. So it is basically releasing heat, and the heat release is actually going to increase the temperature within the gas hydrate stability zone, and it will actually help in dissociating the methane hydrates. Okay, so methane and carbon dioxide replacement is basically a carbon negative, safer gas production technique to produce methane gas from natural gas hydrate reservoirs by injecting pure carbon dioxide or other gas mixtures containing carbon dioxide. So we can actually inject carbon dioxide in the forms of gas, liquid, and also emulsions. Okay. All right, so that would be the four different types of production, methane hydrate production method. And now I'm going to bring you to, I think, about 2 or 3 natural gas hydrates exploration that's been taken place worldwide. Okay, so I'm not going to basically explain more. Okay, just showing to you, okay, what has been done in the gas hydrate exploration. Okay. So to confirm, okay, the occurrence of hydrate bearing sediment, okay, so they've gone through first seismic, okay, and then now they are going into drilling, okay, drilling the site and coring to get the core, the gas hydrate core, to basically estimate how many resources that we have, okay, worldwide. Okay. So presently the explored natural gas hydrate reservoir in the oceanic floor, okay, mainly distribute in Japan, India, Gulf of Mexico, okay, South China Sea. Okay, we have some in South China Sea. Then we have Korea and so Trinidad and Tobago. So for permafrost, okay, it is mainly distributed in Alaska. Okay, we have Mackenzie Delta. Okay, and then we have Qinghai Tibet Plateau in China and also in Siberia. So up to date on the, I think, quite a few countries, okay, have proposed projects on drilling and producing natural gas hydrates. Countries like United States, okay, USA, Canada, Japan, Russia, China, India, and also Korea. See, and then okay, in 2002, okay, if I'm not mistaken, in 2002, okay, so we have the first onshore gas hydrate production test. Okay, it was carried out in Malik site in Mackenzie Delta in the Northwest Territories of Canada. Okay, so in the test, okay, it used the thermal stimulation method. Okay, it used the hot water circulation method. Okay, and I think few years after that, okay, it used a in 2002, they used a thermal circulation method to produce the methane hydrate. And then in, I think 5 years after that, in 2007 and 2008, okay, they proceeded to use a depressurization method in the same site, okay, at the Malik site. Okay, and they found out that depressurization method is more effective than the thermal stimulation method. And not to that it is also cheaper than thermal stimulation method. Okay? So this is basically the locations of the Malik site. Okay, the first onshore production test in Mackenzie Delta in the Northwest Territories of Canada. Okay, then we have India National Gas Hydrate Program Expedition. So this is run together with I think US. Okay, so National Gas Hydrate Program Expedition 1 and 2 is basically the objective is to find, okay, to verify the location of the drill sites to established during the both expeditions. So they found it in the Godavari, okay, where we have that. This is Krishna Godavari Basin, area A, B, okay, and then we have Mahanadi. This is Mahanadi, area A, B, and C. We have Krishna Godavari, and in the Andaman and also in the Andaman Sea, okay, where we have a deep offshore areas of India. So we have when they have gone says expedition and they have drilled, okay, well, okay, to take a course, okay, from the gas hydrate area, but there is no production test that has been carried out yet. Okay, then in Japan, okay, it's not moving. So and then in Japan, okay, it starts off in 2009, okay, and in 2013, okay, 2013, Japan has successfully extracted natural gas, okay, from frozen methane hydrate at this area. Okay, this is what we call as Nankai flow. Okay, they have successfully produced methane hydrate using the pressurization process, but there is basically no commercial or large scale production yet to date. Okay? And then the last one, okay, we have Korean National Gas Hydrate Program. Okay, and this is basically a part of it is located at the Ulying Basin, okay, this area, and it has basically it has drilling expedition, okay, basically to obtain a scientific information about the distribution of the gas hydrate in that basin, okay, and also to calculate or to estimate the resource, and also to identify the suitable site when they are planning to do the production test later on. Okay, and I guess okay that would be the end of my brief introductions to what gas hydrate is, and certainly okay, as a conclusion, gas hydrate could be one of the energy, okay, for the future, okay, but what they have to actually resolve first, I guess, is the cost of actually producing the gas, okay, from the gas hydrate reservoir. Okay, with that, I think, thank you. So we can address questions. Okay, so I'll stop sharing. Thank you for listening. Okay.
Okay, thank you so much, Ms. Maslin. I have just one question that I see here, which
Okay.
is, what do you think about the research being done currently in maybe not maybe in Southeast Asia or the other countries
Okay.
on tackling hydrates? And what is the research current technologies on actually obtaining more hydrocarbon from hydrates?
Okay. Currently, okay, like what I explained, okay, before, okay, we have enormous reserve down there, okay. So, but I think the hindrance is basically the cost. And in order for us to actually produce gas hydrates, okay, in a let's say a commercialized scale, okay, so we need to actually find, okay, the most cost-effective ways of producing the gas hydrates. And I think research to date, okay, they are still trying to find what is the effective technologies to actually to get the gas hydrates, because there are basically factors to be considered, okay, alongside aside from the cost, we have to think also about the environmental impact. Because when we are producing the gas hydrates, okay, we know that gas hydrate is a dangerous to the environment. So to produce it in large scale, okay, without proper planning, I think it's going to be hazardous in a way. Okay, so we have to wait, because I think gas hydrate research is taking off quite lot these days. So hopefully one day, okay, we can be produced in cost effectively, basically. Okay.
Okay, thank you so
So that
much. I
answers the
have
question.
one more question that showed up. How about tackling coal-bed methane? Is it
Mm-hmm.
very common in Malaysia per se?
It is not. It's not yet in common in Malaysia usually, because in Malaysia we don't go into unconventional. We don't tap our unconventional resources yet, because we
But
still
there
go.
is some research being done, to
Yeah.
what I know. Yes. Okay. Okay. I have those two questions that were posted by the audience.
All right.
There's nothing else from from the students, from the public. I would like to thank you, Ms. Maslin, for a wonderful 1 hour of really good information on actually hydrates and the details of hydrates, on the structure of hydrates, and it gives our viewers some chance to actually understand deeper within hydrates. Everybody just thinks that hydrates is just methane with water. So now
Yeah.
we actually understand in detail what hydrates are. Okay. So I would like to thank you, Ms. Maslin,
Okay. Yes, thank
for
you,
joining
Miss
us
Arvin.
today.
Yeah. Thank you,
And
everyone,
thank you
for,
very, very
thank
much.
you, yes,
And
for
we will
joining.
catch up soon. Thank you,
Yes,
Ms.
it's okay.
Maslin.
Thank you very much.
Thank
See you
you.
guys soon, okay?